Have you ever looked up at the night sky and wondered, truly wondered, what lies beyond the edge of our cosmic horizon? We gaze at the stars, trace familiar constellations, and imagine distant galaxies. But the universe holds secrets far deeper and more mysterious than we can see from our small corner of space. So much of what exists remains hidden from our view, just beyond the reach of our most powerful telescopes, teasing us with questions that have no easy answers. Today, we're setting out together on an astronomical adventure to explore 25 of the most baffling space mysteries that challenge everything we think we know about the universe. From the strange behavior of dark matter to the enigmatic whispers of distant black holes, each mystery pulls us deeper into the unknown, inviting us to rethink our place in the cosmos. This journey isn't just about scientific curiosity, it's about connecting to something larger than ourselves, something that has captivated humanity for centuries. Each of these mysteries holds a piece of the puzzle of existence, and as we venture further, you'll start to see the universe not as a static expanse, but as a living, evolving story filled with wonder and possibility. Think about it, every time we uncover one secret, two more appear in its place, reminding us that the cosmos is far stranger and more magnificent than we ever imagined. And that's what makes this exploration so thrilling. It's a reminder that there's always more to discover, always another layer of reality waiting just beyond our current understanding. So settle in and open your mind to the extraordinary. Over the course of this video, we'll traverse cosmic riddles that defy explanation, from ghostly particles that pass through us unnoticed to the unsettling possibility of parallel universes. This is more than a list of facts, it's an invitation to see the universe through the eyes of those who dare to ask the biggest questions. Whether you're a seasoned stargazer or someone who's simply curious about the wonders above, there's something here that will capture your imagination and leave you in awe. Let's begin this journey together, beyond the familiar and into the extraordinary mysteries waiting at the edge of the known cosmos. Our journey into the cosmos begins not with something we can see, but with a force we cannot ignore, a mysterious, colossal pull from the depths of space. Picture our Milky Way galaxy, an immense spiral of stars, gas, and dust, adrift in the vast ocean of the universe. For a long time, we believed it was moving in a relatively predictable way, influenced by the gravitational dance of nearby galactic neighbors. But in the 1970s, astronomers made a startling discovery. By mapping the motions of galaxies across the universe, they realized our entire galactic neighborhood, the Milky Way, along with thousands of other galaxies, is being pulled in a specific direction at an astonishing speed of over 600 kilometers per second. This wasn't just a gentle nudge, it was a cosmic river, and we were all flowing with its current. The source of this immense gravitational pull was dubbed the Great Attractor. This mysterious entity is located in the general direction of the constellations Centaurus and Hydra, but peering directly at it is one of the biggest challenges. It lies behind what astronomers call the zone of avoidance, a region of our own sky that is heavily obscured by the gas, dust, and stars of the Milky Way's central bulge. It's like trying to see a distant city through a thick, persistent fog from our vantage point on Earth. This obscuration has hidden the Great Attractor's true nature from optical telescopes for decades. To peer through this cosmic veil, scientists had to turn to other tools like radio and X-ray telescopes, which can penetrate the dust and reveal the structures hidden behind it. What these instruments have revealed is both awe-inspiring and humbling. The Great Attractor is not a single, monstrous object, but is instead the heart of an enormous concentration of mass known as the Laniakea supercluster, of which our Milky Way is merely a suburban outskirt. This supercluster is a vast web of galaxies, galaxy clusters, and unimaginably large amounts of dark matter, all bound together by gravity. The mass at its core is almost incomprehensible, estimated to be equivalent to tens of thousands of times the mass of our entire Milky Way galaxy, or quadrillions of times the mass of our own Sun. Yet, even with this knowledge, the Great Attractor remains a profound puzzle. The sheer amount of visible matter, the galaxies and gas we can detect, doesn't account for the incredible gravitational strength it possesses. This discrepancy points directly to the dominant yet invisible hand of dark matter, the mysterious substance that makes up most of the universe's mass but does not interact with light. The Great Attractor, therefore, is not just a destination. It's a massive clue in our quest to understand the hidden architecture of the cosmos, a gravitational anchor in the vast, flowing rivers of the cosmic web, reminding us that the universe's greatest forces are often the ones we cannot see. However, the overwhelming pull of the Great Attractor is just one piece of a much larger and more profound cosmic puzzle. This incredible force stems from the gravitational influence of an immense amount of matter, but the truly baffling part is this: most of that matter is completely invisible to us. It neither emits nor reflects nor blocks any form of light. We only know it's there because of its unmistakable gravitational grip on everything we can see. This ghostly substance, which makes up roughly 27% of the entire universe, is what we call dark matter. Its story begins not in the depths of intergalactic space, but within a bustling crowd of galaxies known as the Coma Cluster. Back in 1933, a brilliant and often contentious astronomer named Fritz Zwicky was studying the frantic movements of galaxies within this cluster. He calculated that the combined mass of all the visible stars and gas was nowhere near enough to generate the gravity required to hold these galaxies together. According to the laws of physics, the cluster should have simply flown apart. The only logical conclusion was that there had to be a tremendous amount of unseen mass, what Zwicky called dunkel materie, or dark matter, providing the extra gravitational glue. While many of his peers dismissed the idea, the evidence for this missing mass refused to disappear. The case for dark matter became undeniable decades later thanks to the pioneering work of astronomer Vera Rubin. In the 1970s, she and her colleague Kent Ford were meticulously mapping the rotation speeds of stars within spiral galaxies. They expected stars on the outer edges of a galaxy, much like planets in the far reaches of our solar system, to orbit more slowly than those near the center. But to their astonishment, they found that stars at the very outskirts of galaxies were whipping around just as fast as those near the core. This meant the galaxies contained far more mass than their visible light suggested, and this extra mass was distributed in a massive, invisible halo surrounding the luminous disk of stars. Rubin's work provided stunning confirmation that Zwicky's mysterious dark matter was not just a curiosity in galaxy clusters, but a fundamental component of every single galaxy. So what exactly is this invisible stuff that holds the cosmos together? For decades, the leading hypothesis has pointed to a theoretical class of particles known as WIMP, or weakly interacting massive particles. As their name implies, these particles would have significant mass but interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. This search has spawned some of the most ambitious and sensitive experiments in human history. Deep underground, in mines and tunnels shielded from cosmic rays, detectors like LUX and Xenon 1T wait patiently for the extraordinarily rare ping of a WIMP colliding with an atom of normal matter. Meanwhile, powerful particle smashers like the Large Hadron Collider are trying to literally create dark matter particles by replicating the high-energy conditions of the early universe. Yet, despite these monumental efforts, dark matter particles have never been directly observed. This ongoing mystery has led some scientists to propose alternative theories, suggesting that perhaps we don't need invisible matter at all, but rather a modification of our fundamental understanding of gravity itself. However, the gravitational evidence from galaxy rotations, galaxy clusters, and even the way light bends around massive objects continues to strongly favor the existence of a pervasive, unseen substance. Dark matter is not just a celestial ghost story. It is the invisible scaffolding upon which the entire visible universe is built, its true nature remaining one of the most profound and elusive secrets of the cosmic horizon. But if dark matter is the invisible glue holding the cosmos together, an even more mysterious and dominant force is working in direct opposition, tearing the universe apart at its seams. This force is known as dark energy, and its story represents one of the most shocking paradigm shifts in all of modern science. For much of the 20th century, the prevailing view was that the universe, while expanding from the Big Bang, must be gradually slowing down due to the collective gravitational pull of all the matter within it. The central question for cosmologists was simply whether there was enough matter to eventually halt the expansion and pull everything back in a big crunch, or if the universe would keep expanding forever at an ever-slowing pace. To answer this, two independent teams of astronomers in the late 1990s set out to measure the deceleration rate by observing incredibly distant stellar explosions called Type Ia supernova. These supernovae are crucial because they are what astronomers call standard candles. A Type Ia supernova occurs in a binary star system where a dense white dwarf star steals material from its companion. Once it reaches a very specific critical mass, it undergoes a thermonuclear detonation of such consistent power that every single one of these explosions reaches the same peak brightness. This allows astronomers to use them as cosmic mile markers. By measuring how bright the supernova appears from Earth, they can calculate its distance. And by analyzing the redshift of its light, how much the expanding universe has stretched its wavelengths, they can determine how fast the galaxy containing the supernova was moving away from us at the time of the explosion. The results were not just surprising, they were utterly mind-bending. The data from these incredibly distant supernovae showed that they were significantly fainter, and therefore further away, than their redshifts indicated they should be if the universe's expansion were slowing down. The only possible explanation was that the expansion of the universe wasn't decelerating at all. In fact, it was accelerating. Something was actively pushing galaxies apart from one another with a repulsive force that overpowered gravity itself. This discovery was so monumental that the leaders of the two research teams were awarded the Nobel Prize in Physics in 2011. This mysterious something is what we now call dark energy, and it is estimated to constitute a staggering 68% of the entire mass energy content of the universe, making it the most dominant component of reality. But what is it? The leading explanation harkens back to an idea Albert Einstein himself proposed and later famously discarded: the cosmological constant. In his equations for general relativity, Einstein introduced a repulsive force symbolized by the Greek letter lambda to counter gravity and achieve a static, unchanging universe, which was the belief at the time. When Edwin Hubble later discovered the universe was actually expanding, Einstein called the cosmological constant his greatest blunder. Ironically, modern physics has resurrected the idea, suggesting that this constant might represent a fundamental energy intrinsic to the fabric of empty space itself, a vacuum energy that exerts a negative pressure, causing spacetime to expand at an accelerating rate. Yet the cosmological constant presents a profound dilemma. When physicists attempt to calculate the theoretical value of this vacuum energy using quantum mechanics, the number they get is off by a factor of 10 to the power of 120. This is arguably the worst prediction in the entire history of physics. This colossal discrepancy has led other scientists to propose alternative theories such as quintessence. This model suggests dark energy is not a constant but a dynamic force field that permeates space and could vary in strength over time. Some theories even speculate that this repulsive force could eventually become so powerful that it tears apart galaxies, solar systems, and even atoms themselves in a catastrophic end to the universe known as the Big Rip. Dark energy is the ultimate wild card, a mysterious pressure woven into the vacuum of space that dictates the ultimate fate of everything we see, its true nature remaining one of the greatest and most unsettling puzzles in all of cosmology. Yet as we grapple with the silent, empty sky described by the Fermi paradox, we must also confront the possibility that some cosmic phenomena are not just hidden or silent, but fundamentally undetectable by any means we currently possess. This leads us to one of the most bizarre and counterintuitive predictions of modern physics, an object so dense and gravitationally powerful that it devours light itself, creating a region of space-time from which nothing, not even information, can ever return. The story of the black hole begins not in the depths of space, but with a letter written in the trenches of the First World War. While the grand forces of dark energy sculpt the fate of the cosmos, the search for other intelligent life often focuses on a much smaller, more specific scale, a single, powerful signal that seemed to scream, "We are here," from the depths of the void. On a quiet Ohio evening in August 1977, a radio telescope known as the Big Ear was doing what it had done for years, patiently scanning the sky, its massive ear tuned to the universe's whispers. It was part of the ongoing search for extraterrestrial intelligence, or SETI, a project that sifted through cosmic static hoping to find a pattern, a beacon, anything that could not be explained by natural phenomena. For the most part, the data was a river of noise, but on August 15th, that river delivered a message. The telescope's operation was largely automated, printing its data on continuous reams of paper for astronomers to analyze later. A few days after the detection, a young volunteer researcher named Jerry Amon was poring over the latest printout, line by line. His eyes scanned across columns of letters and numbers representing signal intensity when he came across a sequence that made him stop dead. Amid a sea of single-digit values and blank spaces, one alphanumeric string stood out with shocking intensity, 6EQUJ5. This was the telescope's coded way of representing signal strength. The system used the numbers 1 through 9, and then the letters from A to Z for even stronger readings. This signal had peaked at a value of U, a level of intensity 30 times greater than the background noise of deep space. It was, without any known precedent, a blast of pure, narrowband radio waves. Amon was so astonished that he circled the sequence in red pen and simply wrote, "Wow." In the margin, that exclamation of pure wonder gave the signal its immortal name. The signal's characteristics are what make it so compelling to this day. It was observed on a frequency of 1420.4556 MHz. This is no arbitrary number. It is profoundly significant in astronomy. It is very close to the 21-centimeter line, the precise frequency at which neutral hydrogen, the most abundant element in the universe, naturally emits energy. The logic behind listening at this frequency is brilliant in its simplicity. Any civilization with a rudimentary understanding of astronomy would recognize this as a universal, natural landmark. It's the cosmic equivalent of putting a message on the busiest shipping lane in the ocean, a channel everyone would be monitoring. Furthermore, the signal was extremely narrowband, meaning its energy was concentrated on one specific frequency, unlike the broad-spectrum noise generated by quasars, pulsars, or other celestial objects. This is a hallmark of an engineered transmission. Adding to the mystery was its behavior in the sky. The Big Ear telescope was fixed in place, scanning the sky as the Earth rotated. The wow signal appeared, rose to its incredible peak intensity, and then faded away over a continuous span of 72 seconds. This duration perfectly matches the expected time for a point source to pass through the telescope's beam. confirming it came from a fixed location in space and not from a passing airplane or a ground-based source of interference. All the evidence pointed to a signal of truly extraterrestrial origin. Yet, despite numerous and extensive follow-up searches with far more sensitive equipment, including projects that specifically targeted the same region of space in the constellation Sagittarius, the signal has never been heard again. It was a one-time event, a cosmic door that opened for just 72 seconds and then slammed shut forever. The enduring enigma of the WOW signal fuels endless debate. Could it have been a previously unknown natural phenomenon, a bizarre one-off burst of cosmic radio energy? Perhaps it was a reflection of a human-made satellite off a piece of space debris, though no known satellite was transmitting on that protected frequency. Or the most tantalizing possibility of all, was it a genuine intercepted transmission from an advanced civilization, a fleeting hello that we heard but could not answer or relocate? Its solitary, powerful, and perfectly crafted nature makes it the ultimate celestial ghost story, a reminder that in the vast quiet of the universe, even a single, unexplained whisper can echo for decades, challenging our certainty that we are alone. While the WOW signal remains a singular, unexplained event in the history of cosmic listening, the universe has since revealed a far more common and equally baffling phenomenon, one that unleashes unimaginable power in the blink of an eye. Imagine a flash of radio light so intense that in just a few milliseconds, it can release more energy than our sun puts out over 80 years. These events are not science fiction. They are among the most energetic and mysterious explosions ever detected, known as fast radio bursts or FRB. Their story doesn't begin with a live observation, but with a brilliant piece of scientific detective work in archived data. In 2007, a young doctoral student named David Narkevic and his advisor, Duncan Lorimer, were sifting through old recordings from the Parkes Radio Telescope in Australia. The data was from 6 years prior, gathered during a survey of the Magellanic Clouds. Buried within that mountain of information, they found something utterly anomalous, a 5-millisecond spike of radio energy so powerful it saturated the telescope's detectors. It was unlike anything ever seen, a burst that came from far beyond our own galaxy, a brief shout from the cosmic depths. This first detection, now known as the Lorimer burst, was initially met with skepticism. Could it have been a glitch, a piece of local interference, or maybe even a microwave oven being opened by an observatory staffer? But as years passed, more of these fleeting bursts were found by other telescopes around the world, confirming they were indeed real and indeed cosmic. This opened the floodgates to a whole new field of astronomy. We now know these FRBs are happening all the time. Estimates suggest thousands of them occur across the sky every single day. The mystery deepens when we consider the two distinct types of bursts that have been observed. The vast majority are one-off events, a single, monumental explosion that flashes once and is never heard from again. But a small, fascinating fraction are repeaters. These sources from the same patch of sky fire off multiple bursts with varying strengths and patterns, sometimes in a frantic, storm-like fashion, and other times with long, unpredictable periods of silence in between. This fundamental difference suggests there might be multiple kinds of cosmic engines capable of producing these incredible flashes. So what in the universe could possibly create such a brief yet cataclysmic release of energy? The hunt for answers has led to a spectrum of theories, from the wildly exotic to the profoundly natural. On the more conventional end, the prime suspect is a type of neutron star called a magnetar. These are the remnants of supernova explosions, but they are spinning powerhouses with magnetic fields so incredibly strong they could wipe a credit card clean from halfway to the moon. A starquake on the surface of a magnetar, a sudden cracking of its ultra-dense crust, could theoretically unleash a titanic shockwave, rippling out into space as a blistering flash of radio waves. Other theories involve spectacular cosmic collisions, like two neutron stars merging or a neutron star being consumed by a black hole. Yet, the sheer power and incredible brevity of some bursts have also prompted more speculative ideas. Could we be seeing evidence of immense interstellar light sails being propelled by powerful radio beams, a signature of advanced extraterrestrial technology? While this is considered a less likely possibility, the scientific community agrees it cannot be entirely ruled out without a definitive natural explanation. The true breakthrough in this mystery came not from guessing but from precision. In 2016, astronomers achieved a monumental feat by pinpointing the location of a repeating burst known as FRB 1211-2. Using a coordinated array of telescopes across the globe, they traced its origin not to a massive galaxy, but to a small, faint dwarf galaxy over 3 billion light-years away. More importantly, the burst was localized to a region of that galaxy that is actively forming new stars, an environment perfectly suited for young, violent objects like magnetars. This incredible discovery gave us our first real glimpse into the home of an FRB, providing a crucial clue that these events are likely linked to the life and death of stars. Yet the precise trigger for that millisecond flash of power remains one of the most energetic puzzles on the cosmic horizon. Of all the cosmic mysteries we've encountered, few capture the public imagination quite like the enigma of a distant, flickering star known as KIC 8462852, or as it's more famously called, Tabby Star. Located over 1,400 light-years away in the constellation Cygnus, this otherwise ordinary star became a global sensation not for what we could see, but for the profound and bizarre ways in which its light would inexplicably fade. The story of its discovery is a testament to the power of collective curiosity, beginning not in a professional observatory but with a remarkable citizen science project called Planet Hunters. This initiative, part of the Zooniverse platform, allows anyone with an internet connection to help astronomers sift through the colossal amount of data collected by NASA's Kepler Space Telescope. Kepler's primary mission was to find exoplanets by watching for the telltale, periodic dimming of a star that occurs when an orbiting planet passes in front of it. These dips are typically very small, predictable, and symmetrical, usually on the order of 1% or less of the star's light. But in 2015, a group of volunteers flagged a star whose behavior was anything but typical. They noticed deep, irregular, and asymmetrical dips in its brightness, some as staggering as 22%. This wasn't the signature of a neat, circular planet. It was the chaotic, dramatic dimming of something far more strange and complex. The star was soon named after the lead author of the paper that brought it to the world's attention, Yale astronomer Tabitha Boyajian. The scientific community was immediately captivated and utterly baffled. The light curves from Tabby's star were unlike anything ever observed. The dips were not only extremely deep but also wildly irregular in their timing, duration, and shape. Some lasted for days while others stretched on for weeks. There was no discernible pattern, no periodic rhythm that would point to a simple orbital explanation. Furthermore, analysis of historical photographic plates revealed something even more astonishing. The star's overall brightness appears to have dimmed by a significant amount over the past century. This combination of bizarre short-term dips and a potential long-term dimming presented a puzzle with no clear solution in any astronomy textbook. It was this profound strangeness that led to one of the most thrilling and controversial hypotheses in modern astronomy. Penn State astronomer Jason Wright, along with others, suggested that the irregular dimming pattern was consistent with what we might expect to see from a vast, incomplete swarm of megastructures, a Dyson swarm, built by an advanced Type II civilization to harness the energy of its star. The idea, first proposed by physicist Freeman Dyson, is a staple of science fiction, but here was a real dataset that didn't immediately rule it out. The notion that we might be witnessing the construction project of an alien civilization ignited a media firestorm and captured the world's imagination, turning Tabby Star into a household name and a symbol of the ultimate cosmic what if. Of course, extraordinary claims require extraordinary evidence, and the scientific method quickly went to work. Astronomers pointed their most powerful instruments from the infrared Spitzer Space Telescope to the ground-based Los Cumbres Observatory global network toward the star, hoping to catch it in the act of dimming. The data they gathered began to paint a more nuanced, though still mysterious, picture. Crucially, when the star dimmed in visible light, it dimmed less in infrared light. This is a vital clue. A solid object like an alien megastructure or a planet would block all wavelengths of light equally. However, material made up of fine dust particles like those found in a comet's tail blocks blue light more effectively than red light, which matches the observed pattern perfectly. The prevailing natural explanation now centers on a massive, uneven cloud of dust and debris. One leading theory posits that the star may have recently consumed a planet, causing a catastrophic disruption that sent massive clouds of dusty debris into a highly eccentric orbit. Another suggests a giant swarm of exocomets, perhaps thousands of them, on wild, elliptical orbits that periodically pass in front of the star, blocking its light in those irregular, deep dips. The long-term, century-long dimming could be explained by a larger, more permanent ring of dust in the outer system, casting a slow, persistent shadow. While these explanations are far more conventional than alien engineers, they are no less fascinating. They point to a stellar system in a state of incredible chaos and dynamic activity, a place where planetary formation or destruction is playing out on a scale we've never before witnessed. Tabby Star endures as a powerful reminder that the universe is capable of producing phenomena beyond our immediate understanding, and that sometimes the truth is just as wondrous as any science fiction. While the hunt for extraterrestrial megastructures captures our imagination, some of the most perplexing cosmic mysteries are found much closer to home, hidden in the subtle, unexpected behavior of our own robotic explorers. As the twin Pioneer 10 and Pioneer 11 spacecraft completed their historic missions to Jupiter and Saturn, they began a new, even grander journey, a one-way trip into the abyss of interstellar space. Launched in the early 1970s, these pioneers were the first human-made objects set on a trajectory to leave our solar system entirely. For decades, teams at NASA carefully tracked their positions, using the Deep Space Network to measure their velocity with incredible precision. And that's when they noticed something was deeply wrong. According to the well-established laws of orbital mechanics and gravity, as the probes traveled further from the Sun's gravitational pull should have weakened, causing their outward velocity to decrease at a very specific, predictable rate. But the data told a different story. Both spacecraft were experiencing a tiny, unexpected, and constant deceleration, an additional pull back toward the Sun. This minuscule force, measured at just 8.74 times 10 to the minus 10 meters per second squared, became known as the Pioneer anomaly. To put that number in perspective, it's equivalent to the gravitational pull you'd feel from a single grain of sand held 10,000 kilometers away. Yet, over the vast distances of space travel, this tiny, unaccounted-for tug accumulated into a significant navigation error, placing the probes hundreds of thousands of kilometers off their predicted courses. For nearly 30 years, this anomaly was a thorn in the side of physicists and a source of fascination for those who wondered if we might be on the verge of discovering a new fundamental force or a flaw in our understanding of gravity itself. Could it be evidence of dark matter's gravitational influence within our solar system? Was it a hint that Einstein's theory of general relativity needed a slight modification at very large scales? The implications were profound, suggesting that our maps of the cosmos might be missing a fundamental ingredient. The quest for an answer became a grand puzzle of forensic space science. The pioneers were not designed to be the perfect test subjects for such a measurement. They were engineering marvels of their time, but their design held the key. The leading hypothesis always centered on an onboard source, thermal radiation pressure. The spacecraft were powered by radioisotope thermoelectric generators, which produced a significant amount of heat. This heat was radiated away from the craft's bodies. Crucially, the Pioneer antennas were large, dish-shaped structures pointed directly back at Earth for communication. Engineers realized that heat radiating from the back of these dishes would impart a tiny amount of thrust, like a very weak photon rocket pushing back toward the sun. However, accurately modeling this effect was a Herculean task. It required a complete reconstruction of the spacecraft's thermal blueprint, accounting for every watt of power dissipated by their instruments and every surface from which heat could radiate. The painstaking work of a dedicated team finally paid off. By around 2012, after meticulously analyzing decades of telemetry data and creating exquisitely detailed thermal models, they were able to account for virtually all of the anomalous deceleration. The primary culprit was indeed the recoil force from the anisotropic, or uneven, thermal radiation emitted by the spacecraft. The heat from the nuclear power sources, radiating preferentially from the sides of the craft that faced away from the sun, was gently but constantly braking the probes on their journey to the stars. Yet, even with this robust explanation, a whisper of the mystery remains. Some analyses suggest that after accounting for the thermal effect, a tiny, residual anomaly might still exist, a fraction of the original signal that defies complete explanation. This sliver of uncertainty is a classic hallmark of science at its limits, reminding us that even our most comprehensive models can have subtle blind spots. The story of the Pioneer anomaly is a testament to scientific rigor, a 30-year journey from a bewildering cosmic puzzle to a remarkably mundane yet ingenious engineering solution. It serves as a powerful lesson that before invoking new physics to explain the unknown, we must first exhaustively examine the heat radiating from our own creations. Just when we think we have a handle on the grand architecture of the universe, a discovery comes along that seems to tilt the entire cosmic picture on its side. This brings us to a finding so statistically unsettling and philosophically provocative that astronomers gave it a name fit for a cosmic supervillain: the axis of evil. It all stems from our most detailed baby picture of the universe, the cosmic microwave background, or CMB. This faint, cold glow is the remnant heat from the Big Bang, a snapshot of the universe when it was just 380,000 years old, and it is the very foundation of modern cosmology. The prevailing assumption, supported by overwhelming evidence, is that the universe is isotropic and homogeneous on the largest scales. This cosmological principle means the universe should look the same in every direction, with no preferred location or axis. There should be no up or down in the cosmos, but the axis of evil suggests that on the grandest scale of all, the universe might be subtly pointing a finger right back at us. The story of this cosmic anomaly begins with one of humanity's most sophisticated orbital observatories, the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, its mission was to map the minute temperature fluctuations in the CMB with unprecedented precision. These tiny variations, on the order of 1/100,000th of a degree, represent the seeds from which all cosmic structure, galaxies, clusters, and superclusters would eventually grow. When scientists analyzed the magnificent full sky map produced by WMAP, they found the data beautifully confirmed most aspects of the standard Big Bang model. But in 2005, a team of researchers, including Joe Megiddo and Kate Land, noticed something peculiar, something that should not be there. They discovered that the largest scale fluctuations in the CMB, the biggest waves in the fabric of space-time, were not randomly oriented as expected. Instead, they appeared to be mysteriously aligned with the plane of our solar system and the direction of the sun's motion through space. It was as if the entire observable universe had a faint but undeniable preferred axis, and that axis was bizarrely linked to our own infinitesimally small corner of it. The immediate and most logical suspicion was some form of systematic error. Could this alignment be a ghost in the machine, an artifact introduced by the telescope itself or by our local environment? Perhaps the way the spacecraft scanned the sky, or interference from the Milky Way's own microwave emissions, was imprinting this strange pattern on the data. This is the first and most crucial step in any such discovery, an exhaustive effort to eliminate one's own apparatus as the source of the signal. Yet, after years of intense scrutiny and the subsequent launch of an even more powerful satellite, the Planck mission, the anomaly persisted. The Planck data, released in 2013, confirmed the alignment with even greater confidence. The signal, though faint, refused to be explained away. It seemed the universe itself was presenting us with a coordinate system we never knew existed, and we were sitting at its origin. If this alignment is not an error, its implications are nothing short of revolutionary, challenging the very bedrock of modern cosmology. The cosmological principle is not just a convenient assumption. It is the foundation upon which Einstein's equations and our entire understanding of the universe's evolution are built. If the universe has a preferred axis on its largest scales, it means our place in the cosmos is not merely typical. It is somehow fundamentally special and connected to the whole. This immediately evokes the long-discarded idea of a geocentric universe, not in the literal sense of Earth being the physical center, but in a deeply unsettling philosophical sense that the cosmos might have a structure that correlates with our local frame of reference. Such a finding would force a profound rewrite of our physical theories, potentially pointing toward a pre-Big Bang geometry that set this alignment, or a deeper law of nature that entwines the observer with the observed in a way we have yet to comprehend. The axis of evil stands as a profound and persistent warning that for all our sophisticated models, the cosmos may still be holding its greatest symmetries close to its chest, revealing a universe far stranger and more complex than our principles have so far allowed us to imagine. Moving from the grand, unsettling alignments of the cosmos, we find a profound mystery much closer to home, hidden in the silent, airless rocks brought back from our nearest celestial neighbor. For a world that seems geologically dead, the moon holds a vibrant and puzzling secret from its distant past. When astronauts from the Apollo missions returned with hundreds of pounds of lunar samples, scientists expected to find a world frozen in time, a static relic of the early solar system. But the rocks told a different story. When analyzed, many of these ancient basalts displayed a faint but definitive remnant magnetization. This was a stunning revelation. It meant that the moon, this small, seemingly inert body, once possessed its own global magnetic field, a protective shield generated by a churning, molten core, a lunar dynamo. This presents a monumental puzzle in planetary science. Generating a global magnetic field, or dynamo, requires a specific recipe. A planet must have a core that is at least partially molten. It must be undergoing convection as that hot material rises and cooler material sinks, and it must be rotating with enough speed to twist those convective currents into an organized magnetic field through what's known as the Coriolis effect. For a massive planet like Earth, with a large, still molten iron core and a rapid 24-hour rotation, this process makes perfect sense, but the Moon is a mere fraction of Earth's size and mass. Its small iron core should have cooled and solidified billions of years ago, and its sluggish 27-day rotation provides almost no Coriolis force to spin up a magnetic field. By all our current models of planetary physics, the Moon's ancient dynamo simply should not have existed, yet the evidence from the Apollo samples is unequivocal. It not only existed but was surprisingly powerful, at times even rivaling Earth's magnetic field strength today. So how did our small moon manage to generate this powerful protective force? Astronomers have proposed several compelling theories, each a fascinating glimpse into a more dynamic and violent early solar system. The first theory suggests the Moon's rotation was once much faster. Early in its history, the Moon was likely much closer to Earth, and its orbit would have been significantly different. If it was spinning rapidly in its youth, that faster rotation could have provided the necessary energy to drive a vigorous convection in its core, effectively jump-starting the dynamo before tidal forces from Earth gradually slowed it down to its current pace. This theory paints a picture of a young, energetic moon whirling through space and generating its own protective bubble. Another leading hypothesis points to a far more dramatic source of energy: colossal impact. The early solar system was a shooting gallery, a chaotic environment filled with massive asteroids and planetesimals. A gigantic impact on the lunar surface would have sent seismic shockwaves reverberating through the entire moon. This tremendous energy could have violently stirred the moon's molten core, acting like a colossal spoon that kick-started convection and powered a temporary magnetic field. This would mean the moon's magnetism wasn't a constant feature but rather flared up in brilliant, powerful pulses following the most catastrophic collisions in its history, a shield flickering to life in response to unimaginable violence. A third, and perhaps most elegant, theory involves a profound intimacy between the Earth and the Moon. Billions of years ago, the Moon orbited much closer to our planet. At this proximity, Earth's own powerful magnetic field would have been immense in the lunar sky. Some models suggest that the magnetic field of the young, hot Earth could have been strong enough to induce electric currents within the Moon's own partially molten core. In this scenario, the Moon didn't generate its own field from within so much as it borrowed one from its massive planetary partner, a shared magnetic connection between two worlds locked in a gravitational embrace. This theory implies a time when the Earth and Moon were a truly coupled system, their fates and fundamental forces inextricably linked. Unraveling this mystery is more than an academic exercise. It's a key to understanding planetary evolution everywhere. If a small body like the Moon can sustain a long-lived magnetic field, it forces us to reconsider what conditions might make a world habitable. Magnetic fields protect planetary atmospheres and surfaces from the erosive and damaging effects of the solar wind. The story of the Moon's magnetic past suggests that many more worlds than we thought, even small exoplanets orbiting distant stars, could have once held onto the protective shields necessary for life to emerge. The silent, magnetized rocks in our labs are a testament to a hidden, dynamic chapter in the Moon's life, a reminder that even the most familiar objects in our sky can hold secrets that challenge our understanding of physics itself. Just as the Moon's hidden magnetic history forces us to reconsider the dynamism of seemingly dead worlds, another of our celestial neighbors presents us with a puzzle that is equally tantalizing and deeply frustrating. This mystery unfolds not in ancient rocks, but in the thin, cold air of Mars, where a robotic geologist has been sniffing out a gas that has no business being there. For decades, the question of life on Mars has been a driving force in exploration, and while we haven't found little green men, we may have stumbled upon a potential signature of something living, or perhaps just something equally strange. The story centers on a simple molecule, methane or CH4. On Earth, the vast majority of atmospheric methane is produced by biological processes, from microbes in the guts of cows to decomposing plant matter in wetlands. So when our instruments on Mars began detecting sporadic whiffs of this gas, the scientific community immediately sat up and took notice. The star detective in this story is NASA, a Curiosity rover, a car-sized laboratory that has been trundling through Gale Crater since 2012. Its onboard sample analysis at Mars Instrument Suite, or SAM, is a sophisticated chemistry lab capable of sniffing out trace gases in the Martian atmosphere. And sniff it has. Curiosity's data has revealed something profoundly odd. The methane in its vicinity doesn't linger at a constant background level. Instead, it appears in sudden, unpredictable spikes, sometimes soaring to levels 10 times the baseline before vanishing again within a matter of weeks. Even more intriguing is the discovery of a clear seasonal cycle in the background level of methane, with concentrations peaking during the Martian summer and dropping in the winter. This pattern suggests a complex, ongoing process that is either regularly producing the gas or regularly releasing it from some hidden reservoir. This is where the mystery deepens into a full-blown scientific contradiction. While Curiosity on the ground was reporting these significant bursts and seasonal variations, a powerful orbital sentinel designed specifically for this task was seeing almost nothing. The European Space Agency's ExoMars Trace Gas Orbiter, or TGO, equipped with state-of-the-art spectrometers far more sensitive to atmospheric traces than Curiosity's instruments, began its science mission in 2018. Its primary goal was to perform a definitive global census of methane and other gases. Astonishingly, the TGO has reported that the Martian atmosphere is, for all intents and purposes, devoid of methane, finding none of the large plumes or significant background levels that Curiosity has detected. This stark discrepancy isn't just a minor calibration error. It's a major puzzle that has teams of scientists scrambling for an explanation. How can two of the most advanced chemical laboratories ever sent to another world come to such dramatically different conclusions? The leading theory to resolve this contradiction points to the time of day each instrument performs its measurements. Curiosity operates during the Martian day, while the TGO often makes its measurements when it's flying over the sunlit side of the planet. But its spectroscopy technique works best when looking through the atmosphere at a shallow angle near the day-night terminator. Some scientists propose that very close to the Martian surface, just as the sun rises, tiny amounts of methane might briefly seep out from the soil or from small, localized sources. This methane would then be rapidly destroyed by the intense ultraviolet radiation from the sun, and through chemical reactions with other compounds in the air, dissipating long before it could rise high enough into the atmosphere for the TGO to detect it. In this scenario, Curiosity is the lucky detective who happens to be at the scene of the crime just as it's happening, while the TGO in orbit arrives moments later to find the evidence has already vanished. But if the methane is real, even briefly, where is it coming from? This question splits into two captivating possibilities, one geological, one biological. The geological explanation involves a process called serpentinization. This occurs when certain iron and magnesium-rich rocks like olivine come into contact with water deep underground. A chemical reaction takes place, producing methane as a byproduct. We see this happen on Earth in places like hydrothermal vents. If liquid water still exists in aquifers deep beneath the Martian surface, this process could be slowly producing methane that occasionally seeps up through cracks and fissures in the ground. The biological explanation, however, is what truly fires the imagination. On Earth, countless microorganisms known as methanogens are ancient, primitive life forms that don't require oxygen. Instead, they consume hydrogen and carbon dioxide and exhale methane as a waste product. It's conceivable that similar microbes could have survived for eons in protected subsurface niches on Mars, perhaps in briny water below the permafrost, their metabolic activity producing the tiny, intermittent bursts of gas that Curiosity detects. The seasonal variation could then be explained by changes in surface pressure or temperature that subtly open and close the pathways for this gas to escape. The Martian methane mystery ultimately forces us to confront two equally profound possibilities. Either Mars is far more geologically active and aqueous than we ever believed, with hidden water driving subterranean chemistry we are only just beginning to detect, or we are, against all odds, witnessing the faint but persistent breath of a hidden biosphere, a testament to life's incredible tenacity in the most unexpected of places. While the Martian methane saga unfolds on a nearby world, An event of an entirely different magnitude occurred in 2017, reminding us that some of the universe's greatest mysteries arrive unannounced from the depths of interstellar space. It was first spotted by the Pan-STARRS telescope in Hawaii, a faint speck of light moving at a breathtaking speed. Its trajectory was immediately and stunningly clear. This object was not from our solar system. It was a visitor from another star, the first ever confirmed to pass through our cosmic neighborhood. It was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And true to its name, it delivered a message of profound and puzzling complexity. From the very beginning, Oumuamua defied easy categorization. As astronomers around the world scrambled to observe it, they were met with a cascade of anomalies. The first and most striking was its extreme shape. Based on the way its brightness changed dramatically over time, models indicated it was not a roughly spherical object like most asteroids or comets. Instead, it appeared to be highly elongated, perhaps 10 times longer than it was wide, tumbling end over end through space. This cigar or pancake-like shape was unlike anything naturally occurring in our own solar system, suggesting that the processes which form small bodies around other stars can be radically different from those we understand. The second major puzzle was what it lacked. As it reached its closest approach to the Sun, conventional logic dictated that any icy body should have begun to outgas. Sunlight warming its surface should have vaporized volatile ices, releasing gas and dust to form a classic cometary coma and tail. Yet Oumuamua displayed absolutely no coma. It showed no visible signs of outgassing whatsoever, presenting itself as a completely inert, rocky-looking object. This led to its initial classification as an interstellar asteroid, a curious but seemingly inert rock. But then came the third and most profound anomaly, its motion. As it departed the solar system, precise tracking revealed that Oumuamua was not following a purely gravitational path. It was experiencing a tiny but persistent non-gravitational acceleration, a slight but undeniable push that was ever so slightly altering its trajectory. This is a common feature of active comets, where the jetting of gas from the surface acts like a weak thruster. But Oumuamua had no visible coma, no detectable dust, and no gas signature. It was accelerating without any apparent means of propulsion, a clear violation of the expected rules. This combination of bizarre properties, the strange shape, the lack of a coma, and the mysterious acceleration launched 1,000 theories. The scientific community scrambled to find natural explanations that could account for all the data. One compelling idea proposed that Oumuamua could be a shard of a planet that was torn apart by the gravitational tides of its home star, a violent birth that would explain its elongated shape and lack of surface volatiles. Another, more recent hypothesis suggests it could be a chunk of frozen nitrogen, much like a piece of a Pluto-like exoplanet that was sheared off. As it approached our Sun, the theory goes, the nitrogen ice would have sublimated directly from solid to gas, providing the thrust for the observed acceleration without releasing the dusty debris that would form a traditional comet's tail. However, the most controversial and captivating explanation was put forward by Harvard astrophysicist Avi Loeb. He proposed that the object's unusual acceleration and its extreme shape could be consistent with a light sail, a form of propulsion that uses the radiation pressure from starlight for thrust. In this scenario, Oumuamua would not be a natural object at all, but a piece of advanced technology, perhaps a defunct probe or a discarded remnant from an alien civilization drifting through the galaxy. While this extraterrestrial hypothesis was met with significant skepticism from the broader scientific community, who overwhelmingly favor a natural origin, Loeb forcefully argued that we must remain open to all possibilities when faced with such an anomalous object. He contended that the refusal to even consider an artificial origin is a failure of scientific imagination, especially for an object that displayed multiple characteristics never before seen. The true frustration of the Oumuamua mystery is that we may never have a definitive answer. By the time it was identified, it was already on its way out of the solar system, too faint and too far for further detailed observation. It is now little more than a data point, a collection of tantalizing clues with no way to gather more evidence. Oumuamua serves as a profound and humbling lesson. It showed us that interstellar objects are real and likely common, opening an entirely new field of astronomy. But it also demonstrated that the universe is capable of producing phenomena that challenge our neat categorizations, forcing us to question our assumptions and reminding us that the most extraordinary discoveries are often the ones we are least prepared to explain. As we grapple with these interstellar puzzles and the enigmatic behavior of our own solar system's visitors, we turn our attention to a crisis brewing at the very heart of cosmology itself. A discrepancy so significant it threatens to rewrite our fundamental understanding of the universe's expansion. This is the Hubble tension, a stubborn and growing rift between two of the most trusted methods we have for measuring the cosmos's growth rate. For a century, we've known the universe is expanding, with galaxies racing away from each other as space itself stretches. The speed of this expansion is quantified by the Hubble constant, a single number that represents how fast a galaxy is moving away from us for every megaparsec of distance. Pinpointing this number is arguably the most important goal in modern cosmology, as it tells us the age, size, and ultimate fate of the universe. The shocking problem is that our two most precise ways of measuring it are giving us irreconcilably different answers. On one side, we have a method that peers back to the very infancy of the universe. The Planck Space Telescope mapped the cosmic microwave background, the faint afterglow of the Big Bang, with exquisite detail. By studying the tiny temperature fluctuations in this ancient light, cosmologists can work backwards using our well-tested model of the universe, lambda-CDM, to predict what the expansion rate should be today. This method is incredibly robust and gives us a value of 67.4 kilometers per second per megaparsec. It's a measurement rooted in the pristine physics of the early cosmos. On the other side, we have a technique that builds a cosmic distance ladder in our own galactic neighborhood. This approach, led by the SH0ES team, uses incredibly reliable stars like Cepheid variables and Type Ia supernova as standard candles. We know the true brightness of these objects, so by measuring how bright they appear from Earth, we can calculate their distance with high confidence. By measuring both the distance and the redshift of galaxies containing these stars, we get a direct local measurement of the Hubble constant. This painstaking work yields a value of 73.2 kilometers per second per megaparsec. While this difference of about 5.8 units might seem small, in the world of high-precision cosmology, it's a colossal chasm. The disagreement now stands at a confidence level of 4.4 sigma, meaning there's only about a 1 in 100,000 chance that this is a random fluke. This isn't a minor error bar overlap, it's a full-blown crisis. Scientists have spent years exhaustively checking for systematic errors in both methods. Could there be an unaccounted-for bias in how we measure Cepheid distances? Could our understanding of the primordial plasma in the CMB be slightly off? After a decade of intense scrutiny, the error bars have only shrunk, making the discrepancy more significant, not less. This persistent tension strongly suggests that the problem isn't with our measurements, but with our model. Our standard model of cosmology, lambda-CDM, which has been spectacularly successful for decades, appears to be missing a key ingredient. This realization has launched a new golden age of theoretical physics, as cosmologists propose fascinating and sometimes radical new ideas to explain the tension. One leading possibility involves early dark energy. This theory proposes that a new, additional form of dark energy briefly existed in the first few 100,000 years after the Big Bang. This extra repulsive force would have subtly altered the way sound waves propagated in the early universe, changing the cosmic ruler used to measure the CMB. This would lower the predicted expansion rate from the Planck data, bringing it into line with the higher local measurement. Other theories suggest that dark energy itself is not a constant but is evolving over time, becoming stronger and accelerating the expansion more than our models anticipate. There are even more exotic proposals, such as the idea that dark matter might interact with itself or with radiation in ways we haven't yet considered, or that our universe is ever so slightly curved on the largest scales, subtly warping our measurements. The Hubble tension is more than just a numbers game. It's a profound reminder that our model of the universe is a living, breathing framework, not a finished monument. The fact that two impeccably crafted, independent methods disagree so violently is not a failure of science, but an incredible opportunity. It is the universe itself pointing towards a gap in our knowledge, a hint that there is new physics waiting to be discovered just beyond the edge of our current understanding. Resolving this crisis will require next-generation telescopes like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, which will provide an avalanche of new data to test these wild new theories. The Hubble tension is the most important unsolved problem in cosmology today, and its resolution promises to unveil a deeper, richer, and even more surprising cosmos than the one we think we know. Just as the Hubble tension reveals a crack in our understanding of the universe's grand expansion, a far more local, yet equally baffling, architectural oddity exists right in our own solar backyard. Far beyond the orbit of Neptune, in the cold, dark realm where the Sun is little more than a particularly bright star, lies a vast reservoir of frozen primordial remnants known as the Kuiper Belt. This region is home to dwarf planets like Pluto and thousands of smaller icy bodies, all orbiting in a broad disk. For decades, our models of solar system formation have predicted that this population of objects should continue steadily out to a great distance, gradually thinning out as it merges with the even more distant Oort cloud. But that is not what we see. Instead, at a distance of about 50 astronomical units from the Sun, the Kuiper Belt doesn't gently fade away. It appears to simply fall off a cliff. This sudden and dramatic drop in the number of observed objects is known as the Kuiper Cliff, and it presents a direct challenge to our theories. An astronomical unit, or O, is the average distance from Earth to the Sun, about 150 million kilometers. Neptune orbits at roughly 30 O, and the bulk of the classical Kuiper Belt extends from about 30 to 50 O. Based on the way we believe the solar system formed from a swirling protoplanetary disk of gas and dust, there should be a significant population of icy planetesimals orbiting beyond this 50O boundary. Our simulations predict a smooth, extended disk, yet our telescopes find a stark and unexpected edge. It's as if we were walking through a forest that suddenly and inexplicably turns into an open, empty field, with all the trees neatly lined up at a specific border. The most immediate question is whether this cliff is real or merely an illusion created by our observational limitations. After all, these objects are incredibly faint and enormously far away. Could it be that there are plenty of objects beyond 50O, but they are simply too dark or too small for our current telescopes to detect? This is a perfectly reasonable suspicion, and astronomers have thoroughly investigated it. However, deep sky surveys have successfully detected a number of extreme trans-Neptunian objects with orbits that take them far beyond 50O, proving that our instruments are indeed capable of seeing out there. The problem isn't that we can't see anything past the cliff. It's that we see a tiny fraction of what our models tell us we should be seeing. The drop-off is so severe that it strongly suggests a real physical mechanism is at work, one that has either prevented objects from forming in that region or, more intriguingly, has since cleared them out. This is where the detective work gets truly fascinating, leading to one of the most compelling explanations: the gravitational influence of an unseen, massive planet. The hypothesis suggests that a large world, perhaps 5 to 10 times the mass of Earth, could be orbiting the Sun hundreds of O away on a distant, elongated path. This hypothetical Planet 9, as it has been dubbed, would not only explain the peculiar, clustered orbits of several extreme trans-Neptunian objects, but could also be the architect of the Kuiper Cliff. As this massive planet travels along its eccentric orbit, its immense gravity would act like a celestial shepherd, gravitationally scattering smaller icy bodies that venture too close. Over billions of years, this process could have efficiently ejected a huge number of objects from the region just beyond 50O, either flinging them into the Oort cloud, sending them plunging toward the inner solar system, or hurling them out into interstellar space entirely. This would leave behind the stark, cleaned-out boundary we observe today, yet Planet 9 is not the only potential sculptor of this distant frontier. Other theories look back to the very beginning of the solar system. Perhaps the primordial protoplanetary disk from which all planets formed itself had a sharp edge at around 50O. Maybe the process of planet formation simply ran out of building materials at that distance, or the gravitational stirring from the giant planets in their youth prevented material from coalescing further out. Another intriguing idea involves the Sun's birth cluster. Our star was not born in isolation, but within a crowded nursery of thousands of other young stars. A close pass by another star in this long-ago cluster could have stripped away the outer material of our solar system's disk, truncating it and creating a natural edge that persists to this day. The Kuiper Cliff stands as a stark reminder that even our most familiar cosmic neighborhood still holds profound secrets. Its existence challenges the smooth, predictable models we have constructed and forces us to consider dramatic possibilities, from the lingering gravitational hand of a hidden world to the long-faded echoes of the Sun's violent birth. Unraveling this mystery will require peering even deeper into the frigid darkness at the solar system's edge, a painstaking search for more faint, distant objects whose orbits may finally point the way to the truth. But while we survey the solar system's distant edge for signs of hidden planets, our telescopes have also been capturing a far more energetic and enigmatic signal originating from the very heart of our own galaxy. Deep within the chaotic and crowded core of the Milky Way, a brilliant and puzzling glow has been discovered, one that shines not in visible light but in the most powerful form of energy the universe can produce. This mystery begins with a sophisticated orbital observatory, the Fermi Gamma Ray Space Telescope, which has been scanning the sky since 2008, building the most detailed map ever made of the high-energy universe. Its primary mission is to detect gamma rays, photons carrying billions of times more energy than those of visible light, which are generated by the most violent and extreme events in nature: supernova remnants, active black holes, and colliding neutron stars. When scientists meticulously processed years of Fermi's data, carefully subtracting all the known sources of gamma rays, they expected to be left with a relatively smooth and quiet background. Instead, they found something astonishing. A massive, unexplained excess of gamma-ray radiation was blooming from the galactic center, a diffuse but intense glow extending thousands of light years from the core. This wasn't a point source from a single object. It was a vast, spherical cloud of high-energy light, perfectly centered on the supermassive black hole Sagittarius, a star. Dubbed the galactic center excess, this signal immediately presented a tantalizing puzzle. What incredible process was flooding the core of our galaxy with this immense amount of energy? The hunt for an explanation quickly centered on two captivating and competing theories, each with profound implications. The first and most exhilarating possibility involves the long-sought particles of dark matter. According to this hypothesis, the galactic center is the perfect hunting ground for these elusive entities. We believe dark matter is concentrated in a massive, spherical halo that envelops our entire galaxy, with its density increasing dramatically toward the center. If certain theoretical dark matter particles, like the hypothetical weakly interacting massive particles or WIMP, were to occasionally collide and annihilate each other, the energy released from such an event would produce a shower of standard particles, including gamma rays. The spherical shape and the specific energy signature of the galactic center excess align beautifully with predictions for this kind of dark matter annihilation. For many physicists, this glow could be the first indirect glimpse of the universe's most dominant yet invisible ingredient, the long-awaited signature of dark matter finally revealing itself. However, extraordinary claims require the elimination of all ordinary explanations, and a compelling alternative soon emerged. The galactic center is an incredibly dense and ancient environment teeming with stellar remnants. The second major theory proposes that the excess is not from dark matter at all, but from a vast, unseen population of rapidly spinning neutron stars known as millisecond pulsars. These are the resurrected corpses of dead stars, spun up to incredible speeds by siphoning material from a companion star. As they rotate hundreds of times per second, their powerful magnetic fields beam out lighthouse-like pulses of radiation, including gamma rays. A dense, spherical cluster of thousands of these faint, unresolved pulsars could, in theory, combine to create the exact diffuse glow observed by Fermi. This would be a remarkable discovery in its own right, revealing a previously unknown population of ancient stellar objects lurking in the galactic bulge. Distinguishing between these two theories has proven to be a monumental challenge in astrophysical detective work. The Fermi data, for all its precision, shows a glow that is frustratingly smooth. If the excess were caused by individual pulsars, advanced statistical analyses suggest we might expect to see at least some slight lumpiness or pinpoint sources within the haze. The fact that the signal appears so smooth lends weight to the dark matter interpretation. Yet, as telescope sensitivity improves, astronomers are beginning to find faint point sources within the excess, potential millisecond pulsars that could account for at least a portion of the signal. This has led to a fascinating third possibility. The answer might not be a simple either-or. The galactic center excess could be a complex cocktail, a blend of radiation from both a population of ancient pulsars and the annihilation of dark matter particles. Unraveling this cosmic recipe will require even more precise observations from next-generation gamma-ray telescopes and gravitational wave observatories that can peer into the dynamic heart of our galaxy with unprecedented clarity. This mysterious glow represents a fundamental crossroads in astronomy, where the answer could either unveil the true nature of dark matter or reveal an entirely new chapter in the life cycle of stars, all emanating from the brilliant, violent core of our Milky Way. And just as we search for the source of a mysterious glow at our galaxy's heart, we must confront an even more fundamental cosmic inventory problem, one where the universe itself seems to have misplaced a staggering amount of its most basic building blocks. This is the mystery of the missing baryons. Baryons are the family of particles that make up all the ordinary matter we know and love, the protons and neutrons in every atom of every star, planet, and person. Our most robust theory for the origin of the elements, known as Big Bang nucleosynthesis, provides a very precise prediction. It tells us exactly how much of this ordinary, baryonic matter should have been created in the fiery first minutes of the universe. When we add up all the matter, we can directly see all the stars shining in galaxies, all the glowing gas and obscuring dust, everything we've ever observed with our telescopes. We come up shockingly short. We can only account for less than half of the baryonic matter that our models insist must be out there. It's as if the universe did its shopping, brought home bags full of groceries, but over half of them vanished between the store and the kitchen. This isn't a dark matter problem. This is a crisis of the ordinary, the luminous, the stuff we are made of simply being gone. So where could an entire universe's worth of atoms be hiding? The leading suspect isn't found in the bright, dense centers of galaxies, but in the vast, empty deserts between them. For decades, cosmologists have theorized that the missing matter must be woven into the cosmic web itself, a faint, diffuse network of incredibly hot gas that fills the space between galaxies. This theoretical reservoir has a name, the Warm Hot Intergalactic Medium, or WIM. Picture the universe's large-scale structure not as a collection of isolated islands, but as a colossal sponge. Galaxies and clusters are the dense knots, but they are connected by an intricate web of invisible filaments, and it is within these million-degree rivers of gas that the missing baryons are believed to reside. The gas is so hot it is fully ionized, meaning its electrons have been stripped from their atoms, making it completely invisible to optical telescopes that look for the telltale signature of neutral hydrogen. It's also so incredibly diffuse, with maybe only a few dozen particles per cubic meter, that it doesn't emit enough radiation for our instruments to easily pick up. It is the ultimate cosmic camouflage, a ghostly haze of matter that has remained virtually undetectable by conventional means. Finding something that is both incredibly hot and incredibly faint requires extraordinary ingenuity, and astronomers have risen to the challenge with brilliant indirect detection methods. One powerful technique utilizes the Sunyaev-Zeldovich effect. This occurs when the faint photons of the cosmic microwave background, the ancient afterglow of the Big Bang, travel across the universe on their way to our telescopes. If these photons pass through a region of hot, ionized gas like a filament of the WIM, they get a tiny energy boost from interacting with the energetic electrons within that gas. This subtle interaction leaves a specific, measurable imprint on the CMB light, a spectral distortion that acts like a shadow, revealing the presence and properties of the otherwise invisible gas cloud. It's like detecting a nearly invisible pane of glass by noticing how it very slightly warps and distorts the view of the landscape behind it. Another, more recent technique harnesses the power of the universe's most energetic messengers, fast radio bursts. As these brilliant millisecond flashes of radio waves travel billions of light years across the cosmos, their journey isn't unimpeded. They pass through all the ionized material that lies between their source and our telescopes. This intervening material causes a delay in the burst's arrival time, a phenomenon called dispersion, where lower frequency radio waves are slowed down more than higher frequency ones. By meticulously measuring this dispersion, astronomers can calculate the total number of free electrons the burst encountered along its path, a direct measure of the amount of ionized gas it traveled through. By analyzing the signals from many FRBs coming from different distances and directions, scientists can begin to map out the distribution of this diffuse material throughout the cosmic web, effectively using these brilliant flashes as backlights to illuminate the shadowy filaments of the WIM. The evidence gathered from these and other methods is now painting a convincing picture. We are finally beginning to account for the universe's missing matter, finding it in the form of this seething, tenuous ocean of gas that permeates the spaces between the galaxies. This discovery closes a major chapter in cosmology, confirming that the ordinary matter predicted by our theories does indeed exist. Yet, it simultaneously opens a new one, shifting the mystery from if the baryons exist to how this warm, hot intergalactic medium is structured, heated, and maintained within the grand architecture of the cosmic web. Solving the case of the missing baryons doesn't diminish the wonder. It reveals a universe far more intricate and interconnected than we ever imagined, where the empty void of space is in fact a vibrant, dynamic, and hidden reservoir of creation. But if we have successfully mapped the cosmic web to find the universe's missing ordinary matter, a different kind of inventory problem persists, one that reaches back to the universe's very first minutes and involves one of the most fundamental elements of all. The story of our origins is written in the elements, and for the most part, the cosmic ledger balances beautifully. When we look at the oldest stars in the universe, relics from the dawn of time, their composition matches the stunningly accurate predictions of a process called Big Bang nucleosynthesis. This theory describes how, in the first 20 minutes after the Big Bang, the entire universe was a searingly hot fusion reactor, forging the lightest elements from a primordial soup of protons and neutrons. The calculations for how much hydrogen, helium, and deuterium should have been created are a crowning achievement of modern cosmology, matching observation with near-perfect precision. But there is one glaring, persistent exception, a single line in the cosmic recipe that has been crossed out and scribbled over by reality. The universe is missing its lithium. According to the models, that initial cosmic forge should have produced a specific, measurable amount of a lithium isotope called lithium-7. Yet, when astronomers measure the lithium content in the atmospheres of the most ancient stars in the Milky Way's halo stars that formed from nearly pure primordial gas and have therefore preserved that original chemical signature, they find only about 1/3 to 1/2 of the predicted amount. It's not a small discrepancy, it's a factor of 2 to 3, a huge gap that has stubbornly resisted explanation for decades. This is the lithium problem, and it represents a fundamental crack in our otherwise pristine understanding of the universe's first moments. It suggests that either our understanding of nuclear physics in that extreme environment is incomplete, or that something profound happened to the lithium after it was created, or even that an entirely unknown process was at work in the infant cosmos. Scientists have pursued 3 main avenues to solve this puzzle, each more fascinating than the last. The first path questions our nuclear knowledge. Could the reaction rates used in the models for key processes be slightly off? The primordial fusion that created lithium-7 is a delicate chain of events, and a miscalculation in the probability of one specific nuclear interaction could throw off the entire final tally. However, laboratory experiments have repeatedly refined these rates, and while they have narrowed the error bars, they haven't closed the gap. The nuclear physics, as we currently understand it, seems solid, pointing the finger elsewhere. This leads to the second possibility, stellar destruction. Perhaps the lithium was created in the correct amount, but it was subsequently destroyed in those very same ancient stars we used to measure it. These old stars are not completely inert. They have convective outer layers that can drag material from the surface down into the hotter interior, where temperatures are high enough to burn lithium. It's possible that over their billions of years of life, these stars have systematically depleted their original lithium supply. The challenge for this theory is that it requires a very specific and efficient mixing process to occur in almost all ancient stars, a universal behavior that has been difficult to confirm through stellar models. The third and most thrilling category of solutions involves new physics. Could the lack of lithium be a signature of something exotic that occurred in the early universe? One compelling idea involves hypothetical particles known as actions, which are candidates for dark matter. If they existed in the early universe, they could have drained energy from the primordial plasma, effectively cooling it down slightly and altering the precise conditions under which nucleosynthesis occurred, potentially suppressing lithium production. Another radical proposal suggests the decay of unknown, massive particles from the first second of the universe could have injected energy or neutrons into the mix, throwing a wrench into the well-orchestrated fusion chain. The lithium problem thus stands as a tiny but profound clue, a single element out of place that may be our best window into the physics that operated in the most inaccessible and energetic period of cosmic history, a silent witness to processes we have yet to imagine. Moving from the intricate cosmic web that holds the missing matter of the universe, we encounter a region of space so profoundly empty it defies our very understanding of cosmic structure. Imagine a sphere of nothingness so vast it could contain thousands of galaxies like our Milky Way, yet holds almost none. This is the Boötes Void, one of the largest and most perplexing supervoids ever discovered, a gaping hole in the fabric of the cosmos that challenges our most fundamental ideas about how the universe is organized. Its discovery in the early 1980s by astronomer Robert Kirshner and his team was a moment of pure astonishment. While conducting a redshift survey to map the distribution of galaxies, they found a region in the constellation of Boötes that was shockingly, unnervingly dark. Where their instruments expected to record the telltale signs of thousands of galaxies, they found only a handful of lonely points of light in an ocean of black. The scale of this emptiness is almost impossible to comprehend. The void spans an estimated 330 million light-years across. To put that in perspective, if you were to place our Milky Way galaxy at one edge of this void, the Andromeda galaxy would be a mere speck 2.5 million light-years away. The other side of the Boötes void is over 130 times that distance, a sheer, staggering expanse of near total nothingness. The existence of such a void presents a direct and formidable challenge to the cosmological principle, the foundational idea that on the largest scales, the universe is homogeneous and isotropic. It should look roughly the same in every direction. While we expect some variation with dense clusters of galaxies and emptier voids, the scale of the Boötes void is so extreme it seems to violate this principle. Our standard model of cosmology, lambda cold dark matter, does predict that the gravitational pull of dark matter will sculpt the visible universe into a vast cosmic web, an intricate lattice of dense filaments and emptier voids. However, computer simulations of this process consistently fail to produce voids as immense and as empty as the one in Boötes. According to these models, such a colossal underdense region simply shouldn't exist. The gravitational tug from the immense masses of surrounding superclusters should have prevented a void of this magnitude from ever forming, or it should have been filled in by now with galaxies flowing in from denser regions. The fact that it persists is a major puzzle, suggesting either a flaw in our understanding of gravity and structure formation, or that we are witnessing a statistical anomaly of truly cosmic proportions. Initially, the void was thought to be almost completely barren, with early estimates suggesting only a few dozen galaxies resided within its incredible volume. More recent and sensitive surveys have since identified more galaxies closer to 60, but this is still a number so vanishingly small it only deepens the mystery. It's like finding a mere 60 pebbles scattered across a desert the size of Texas. The galaxies that do call the void home are fascinating in their own right, often isolated and evolving in profound isolation, untouched by the gravitational interactions and mergers that shape galaxies in denser environments. These lonely islands in the void could be crucial laboratories for understanding galactic evolution in the most extreme conditions imaginable. The pressing question remains, how did this void get so empty? One compelling theory suggests it may not be a simple, spherical void at all, but rather the convergence of several smaller voids, a chance intersection of bubbles in the cosmic foam that from our vantage point appears as one giant cavern. Another, more speculative idea proposes that the Boötes void could be the result of an ancient and unimaginably vast collision between regions of matter and antimatter in the very early universe, a cataclysm that would have annihilated everything in its path, leaving behind a legacy of pure emptiness. The Boötes void stands as a humbling reminder of the universe's capacity for surprise. It forces us to question whether our standard model, for all its successes, is complete, or if we are missing a crucial piece of physics that governs the growth of structure on the very largest scales. It is a testament to the fact that even emptiness holds profound secrets, and that the greatest cosmic mysteries are often found not in the brilliant clusters of matter, but in the vast, silent spaces between them. While the Boötes void represents a staggering emptiness in the cosmos, the universe also sends us messengers of unimaginable power, particles that carry more energy in a single subatomic package than a professionally thrown fastball. These are ultra-high-energy cosmic rays, and their existence pushes the very laws of physics to their absolute limit. Imagine a single proton, a fundamental building block of matter, traveling through the vacuum of space at a velocity so close to the speed of light that it possesses kinetic energy equivalent to 100 million times the power achievable in the largest human-made particle accelerator, the Large Hadron Collider. These are not just theoretical curiosities, they are real particles that slam into the top of our atmosphere with the force of a well-hit tennis ball, all concentrated into a size a million times smaller. The sheer existence of such particles is a profound mystery, and their origins are one of the most sought-after prizes in modern astrophysics. The puzzle deepens considerably with a fundamental prediction from physics known as the GZK cutoff, named for physicists Greisen, Zatsepin, and Kuzmin. In the 1960s, they calculated that any proton traveling through the universe with an energy greater than about 10 to the 20th power electron volts should not be able to reach us from very far away. The reason is the cosmic microwave background radiation, that faint relic heat from the Big Bang that fills all of space. For an ultra-high-energy proton, this background radiation is no longer a harmless microwave glow. It appears as a dense wall of high-energy gamma rays. As the proton travels, it should constantly collide with these photons. Each collision would be like a speeding bullet hitting a brick wall, robbing the proton of its energy through a process called pion production. According to this ironclad law of physics, any cosmic ray we detect with energy above this GZK cutoff must have originated from within our local cosmic neighborhood, within a radius of roughly 150 million light-years. This creates a manageable hunting ground, a volume of space we can reasonably survey for the most violent and powerful engines in the universe. Yet, when we point our most sophisticated detectors toward the skies, the picture becomes incredibly murky. Massive observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah use thousands of sensors spread over hundreds of square miles to catch the extensive air showers created when these cosmic rays hit our atmosphere. They can pinpoint the energy and the rough direction from which the particle came. The baffling result is that the trajectories of these ultra-high-energy events do not consistently point back to any obvious cataclysmic source within that 150 million light-year bubble. There is no nearby supernova remnant, brilliant quasar, or colossal galaxy merger sitting neatly at the point of origin for most of these events. It's as if we are finding cannonballs in a field, but the cannons that fired them are nowhere to be seen. The leading suspects for these cosmic accelerators are some of the most extreme objects known to science. At the top of the list are active galactic nuclei, the supermassive black holes at the centers of galaxies that are actively devouring matter. As vast disks of superheated gas spiral into the black hole, powerful magnetic fields could act like gigantic slingshots, flinging particles outward to near-light speeds along colossal jets that extend for thousands of light-years. Another prime candidate is the gamma-ray burst, the most energetic explosion since the Big Bang itself, thought to mark the birth of a black hole or the collision of two neutron stars. The relativistic shockwaves from such an event could, in theory, accelerate particles to these phenomenal energies. However, these events are rare and fleeting, and matching a specific ultra-high-energy cosmic ray to a past gamma-ray burst has proven exceedingly difficult. The key reason for this frustrating lack of a clear source lies in the invisible magnetic fields that permeate the vast spaces between galaxies. These fields, though incredibly weak, are woven throughout the entire cosmic web. A proton, being a charged particle, does not travel in a straight line from its source to Earth. Instead, it is constantly deflected and bent by these magnetic fields, tracing a chaotic, corkscrew path across the universe. By the time it reaches us, its direction of arrival is essentially random, pointing back not to its true source, but to the last curve in its long and winding road. This is the ultimate cosmic shell game, where the source of the particle is hidden not by distance, but by the invisible maze of magnetism it had to navigate. Unraveling this mystery will require not just detecting more of these rare events to statistically triangulate their origins, but also creating a far better map of the extragalactic magnetic fields that scramble their signals, a painstaking effort to chart the invisible currents that guide the most powerful particles in the universe. While we search the galaxy for elusive particles and map the largest voids in existence, one of the most stunningly precise geometric patterns in the solar system has been whirling right above our heads, a masterpiece of atmospheric physics painted on a planetary scale. At Saturn's North Pole, a colossal six-sided jet stream dominates the weather, a hexagon so vast it could comfortably fit 4 Earths side by side within its boundaries. This isn't a fleeting cloud formation or a trick of the light. It's a persistent, towering structure of swirling winds, a hurricane-like storm at its center, and walls of cloud that plunge dozens of kilometers down into the planet's depths. Its discovery was as serendipitous as it was shocking. When the Voyager spacecraft flew past Saturn in the early 1980s, its cameras were only able to capture the planet's northern hemisphere in dim light. But amid the gloom, mission scientists spotted something unbelievable, a distinctly hexagonal pattern in the clouds. For years, it was debated, a curiosity that some dismissed as a temporary atmospheric fluke or a mere imaging artifact. Decades later, NASA Cassini spacecraft arrived at Saturn for a long-term mission, and it patiently waited for the northern hemisphere to emerge from its long winter darkness. When the sunlight finally returned, Cassini's high-resolution cameras and instruments turned north and confirmed the impossible. The hexagon was not only still there, but it had remained perfectly stable, maintaining its precise six-sided shape and seemingly locked to the planet's internal rotation rate for over 30 Earth years and likely much longer. This wasn't a fluke, it was a fundamental feature of Saturn's atmosphere, a permanent landmark on a world without a solid surface. The sheer scale is breathtaking. Each side of the hexagon is longer than the diameter of Earth, and the winds that form its perimeter race at speeds over 320 kilometers per hour. Yet the structure itself rotates with a stately, unchanging rhythm once every 10 hours and 39 minutes. How does a fluid, chaotic system like a planetary atmosphere spontaneously generate and maintain such a stark geometric shape? The answer seems to lie not in magic, but in the elegant rules of fluid dynamics. Researchers have turned to the laboratory to recreate the conditions that might birth a hexagon. In a fascinating experiment, a circular tank representing a planet's polar region is filled with water and placed on a rotating table to simulate planetary spin. When a smaller, independent ring at the center is spun at a different, faster rate, it creates a shear zone between the two rotating fluids. As the speed differential increases, the fluid naturally begins to organize itself into stable, standing waves. Just by adjusting the relative speeds, scientists can make the fluid form a perfect polygon, 3 sides, 4, 5, and most commonly 6. The hexagon emerges as a preferred stable state under specific conditions, a self-organizing pattern that arises from the complex interplay of forces. This suggests that deep within Saturn's churning hydrogen and helium atmosphere, a similar process is at work. A powerful eastward jet stream, like the one powering the hexagon's perimeter, likely exists at that specific latitude. The differences in wind speed between this jet and the surrounding, slower-moving atmosphere create a steep velocity gradient. On a rapidly rotating planet like Saturn, the Coriolis effect, the same force that dictates the rotation of hurricanes on Earth, strongly influences these shear instabilities. The combination of the jet stream's speed, the planet's rapid rotation, and the depth of the atmosphere appears to be the perfect recipe for locking this turbulent system into a stable, 6-lobed standing wave pattern. The hexagon is essentially a colossal, permanent atmospheric ripple frozen in place by physics. This naturally leads to a compelling question. If this is a straightforward process of fluid dynamics, why don't we see similar geometric patterns at the poles of other planets? Jupiter, another gas giant, has chaotic, swirling polar storms but no giant polygons. The answer highlights the unique conditions on Saturn. Jupiter is massive and rotates quickly, but its atmospheric jet streams are far more numerous and turbulent, perhaps preventing a single, stable pattern from dominating. Saturn, by contrast, seems to have a simpler, more orderly system of broader jets, providing a cleaner canvas for a standing wave to form. Even on Earth, with its slower rotation and a rocky surface that creates friction and disrupts large-scale flow, such a phenomenon is impossible. The Saturn hexagon stands as a stunning example of how the universal laws of physics can manifest in wildly different ways depending on a world's specific ingredients, its size, its spin, and the depth of its air. It is a natural sculpture carved not by wind alone, but by the fundamental mathematics of motion itself, a reminder that even in the chaos of a gas giant sky, hidden order awaits discovery. Yet as Saturn's hexagon reveals the hidden geometric order within chaotic fluids, another structure far out in the depths of space presents a shape so precise and angular it seems almost manufactured. This is the Red Rectangle Nebula, a cosmic artifact so uniquely structured that when astronomers first glimpsed it, they could scarcely believe it was natural. Located about 2,300 light-years from Earth in the constellation Monoceros, this nebula surrounds a dying binary star system known as HD 44179. Its name comes directly from its appearance on early photographic plates taken in the 1970s, which showed a strikingly rectangular shape glowing with a deep, ruddy hue. In a universe dominated by spheres, spirals, and chaotic clouds, the red rectangle's sharp angles and symmetry are a profound anomaly, a geometric rebel that defies our standard models of how planetary nebulas form and evolve. The story of its discovery begins in 1973 during a rocket flight designed to survey the sky in ultraviolet light. The Wisconsin Ultraviolet Photopolarimeter Experiment, or WUP, was tasked with studying the polarization of UV light from celestial objects. When the data from the star HD 44179 came back, it revealed something completely unexpected. The light wasn't just polarized, it was highly polarized in a way that suggested it was being scattered by an unusually large amount of dust, and in a very specific, non-spherical configuration. Ground-based telescopes were then pointed at the coordinates, and the first images confirmed the incredible truth. The star was nestled at the center of a vast, glowing structure with a near-perfect X-shape, all enclosed within a strikingly rectangular boundary of luminous gas. It was unlike any other nebula ever catalogued. So how does a dying star create such a sharp-cornered masterpiece? The answer lies in the intricate dance between the two stars at its heart and the physics of their demise. HD 44179 is not a single star, it's a close binary system. One of the stars is a post-asymptotic giant branch star, meaning it has already shed its outer layers and is well on its way to becoming a white dwarf. Its companion is a smaller main sequence star. As the larger star began to die, it started expelling its outer layers into space in a process that would normally create a spherical nebula. However, the gravitational influence of the companion star dramatically alters this process. Instead of a serene, outward flow, the material is funneled into two powerful, opposing jets that shoot out from the star's poles, creating what astrophysicists call a bipolar outflow. But the red rectangle is far more complex than a simple hourglass shape. The true secret to its angular form is a dense, surrounding disk of dust and gas that orbits the binary pair. This torus or donut-shaped disk is incredibly thick and acts like a stencil, constricting the outflowing material. Imagine trying to squeeze a thick fluid through a small, circular hole. It would naturally form a jet. Now imagine that the hole isn't a clean circle but has a distinct shape. In the case of the red rectangle, the disk is so thick and the outflow is so constrained that the material isn't able to expand spherically. Instead, it rushes out above and below the disk but is tightly collimated by it, creating two conical lobes that are pointed directly at us. Our vantage point, looking almost directly down the axis of this system, makes these two cones appear to overlap, their edges tracing the straight, diagonal lines of a large X. The sharp rectangular boundary we see is simply the projected outline of these two cones viewed side-on, a trick of perspective that transforms a three-dimensional flow into a two-dimensional geometric wonder. The breathtaking concentric rings or rungs that give the nebula the appearance of a celestial ladder are another layer of its mystery. These are not static shells of gas, they are a historical record of the star's final act. The binary system is precessing, meaning the axis of rotation is slowly wobbling like a spinning top. As the star ejects material in its bipolar jets, this wobble causes the direction of the outflows to trace a slight circular path over time. Each pulse of ejected material expands outward, and the next pulse, launched from a slightly different angle due to the precession, expands inside it. This creates a series of nested, expanding bubbles that, from our edge-on perspective, appear as those precise, equidistant lines. It's a cosmic echo, a natural timestamp of the system's rhythmic death throws over thousands of years. The profound rarity of such a sharply defined structure tells us that the red rectangle is a snapshot of a very brief and very special phase in stellar evolution. It requires a perfect storm of conditions, a binary system with a specific mass ratio, a thick dust disk formed from the material of the dying star, and a vantage point that aligns almost perfectly with the system's axis. This combination is so unlikely that we've found very few other examples, making the red rectangle a precious laboratory. It teaches us that the final stages of a star's life are not always a chaotic explosion, but can be a controlled, almost artistic release of energy, sculpted by gravity and spin into a temporary monument of geometric perfection. This nebula is a testament to the hidden order within cosmic chaos, a reminder that the universe's beauty often lies in the intricate interplay of physical laws. While Saturn's geometric perfection and the red rectangle's angular artistry reveal a cosmos governed by elegant physical laws, another discovery plunges us into a paradox that seems to tear the very rulebook of reality in half. This is not a mystery of missing matter or unseen planets, but a fundamental conflict between the two most successful theories in all of physics, a crisis triggered by the most destructive objects in the universe. It began with a stunning realization by Stephen Hawking in the 1970s, an insight so troubling it has haunted theoretical physics for half a century. Black holes, it seems, are Chinese letter S ultimate shredders, and they appear to destroy information. To understand why this is so catastrophic, you first have to understand what physicists mean by information. It's not a book or a hard drive. In quantum mechanics, information refers to the specific, unique quantum state of every single particle, its spin, its charge, its momentum. A core, unshakable principle of quantum theory is that this information is never truly lost. It can be scrambled, spread out, and become incredibly difficult to read, but it is always, in principle, recoverable. This is known as unitarity. If you could somehow reverse all the interactions of every particle in a smoking pile of ash, you could, in theory, reconstruct the original book that was burned. The information is preserved within the ash, however chaotically. This is a foundational pillar of our understanding of the universe. Hawking's breakthrough was to apply quantum theory to the edge of a black hole, and what he found seemed to violate this sacred principle. He calculated that black holes are not completely black. They slowly emit a faint glow of radiation, now famously known as Hawking radiation. This radiation, he argued, is entirely thermal. Its properties, its energy and temperature, depend only on the black hole's mass, charge, and spin. It carries no other details. It doesn't matter if the black hole was formed from a collapsed star made of hydrogen or from a giant, compressed encyclopedia. the Hawking radiation it emits would be identical. This means that when a black hole eventually evaporates completely after eons of emitting this radiation, all that remains is this generic thermal glow. The specific quantum information about all the trillions of particles that ever fell in is seemingly erased from the universe forever. This is the black hole information paradox. The laws of general relativity that govern black holes seem to demand information destruction, while the laws of quantum mechanics absolutely forbid it. For decades, this was the Gordian knot of theoretical physics. How could these two pillars of modern science be so irreconcilably wrong? The most promising solution to emerge is as mind-bending as the paradox itself, the holographic principle. This idea proposes that all the information that falls into a black hole is not lost inside its volume, but is instead encoded on its two-dimensional boundary, the event horizon. Think of it like a cosmic piece of holographic film. A hologram is a two-dimensional surface, but when you shine a light through it, it projects a three-dimensional image. The holographic principle suggests that our perception of a three-dimensional world inside the black hole might actually be a projection from a two-dimensional description painted on its surface. Every particle that falls in leaves an imprint on this stretched horizon, like a fingerprint on a soap bubble, preserving its information in a form we just don't yet know how to decode. This elegant idea, however, spawned a new and equally violent paradox, the firewall paradox. If information is preserved on the event horizon, what does that mean for someone falling in? According to Einstein's equivalence principle, an astronaut crossing the event horizon of a sufficiently large black hole should feel nothing special. It should be an uneventful, if terminal, journey. But if the horizon is a blazingly energetic membrane encoding all that information, it would be anything but smooth. It would be a searing wall of fire, a firewall, that would instantly incinerate the astronaut. So we are left with a terrible choice. Either quantum mechanics is wrong and information is destroyed, or general relativity is wrong and the event horizon is a deadly singularity of energy. You cannot have both safety for the falling observer and preservation of information. The laws of physics seem to demand we sacrifice one. The quest to resolve this has driven the most cutting-edge work in theoretical physics, particularly in string theory and the study of quantum gravity. Recent developments offer a glimmer of a solution, suggesting that the interior of a black hole is far more complex than a simple empty space. Through mathematical techniques like the AD/CFT correspondence, physicists have found that the information within a black hole might be so thoroughly scrambled and entangled with the Hawking radiation it emits that it is, in fact, preserved, but in a form that is incredibly complex to unravel. The radiation may not be purely thermal after all. Subtle correlations between the escaping photons could carry the hidden signature of the information that fell in. It would be like burning that encyclopedia and, instead of being left with ash, discovering that the heat and light rising from the flames contain, in their intricate patterns, the entire text of every page. The information is never gone, it is just transferred into the most complex cryptogram imaginable. The black hole information paradox is more than an abstract puzzle for physicists. It is a direct assault on our understanding of reality, forcing us to confront whether the universe is fundamentally predictable and orderly, or if at its heart, in the darkest of places, there lies a fundamental randomness that destroys the past. Unraveling this mystery is not just about saving information. It's about discovering the true, unified language of the cosmos, a set of laws that can seamlessly weave the fabric of space-time with the quantum code that underpins it all. It is a battle for the soul of physics, fought on the edge of oblivion. But if black holes seem to challenge the very laws of reality, a far more subtle and beautiful phenomenon closer to home presents a mystery not of missing information, but of an unexpected surplus. For centuries, sky watchers in dark, clear locations have witnessed a hauntingly beautiful sight in the eastern sky just before dawn or in the west just after sunset. Appearing as a faint, ethereal pyramid of soft light stretching upward from the horizon, this glow is known as the zodiacal light. It is sunlight scattered by countless trillions of microscopic dust particles that populate the inner solar system, tracing out the plane of the ecliptic where the planets orbit. For a long time, this was considered a charming but understood feature of our cosmic neighborhood, a remnant of the solar system's formation, a cloud of dust steadily replenished by crumbling asteroids and the tails of passing comets. However, when we began to actually quantify this dust, a serious problem emerged. Our best models of the solar system's dusty inventory, based on the known rates of cometary disintegration and asteroid collisions, simply cannot account for the sheer volume of material needed to produce the intense glow we observe. We are surrounded by a phenomenal amount of dust, and we have no clear idea where most of it is coming from. This zodiacal light paradox forces us to reconsider the dynamics of our own celestial backyard. The interplanetary dust cloud is not a static museum piece. It is a dynamic, evolving environment. Dust particles are constantly being lost. They spiral inward toward the sun due to a subtle drag force called the Poynting-Robertson effect, where the mere pressure of sunlight itself acts as a brake on their orbital motion. They collide with each other, grinding down into ever smaller fragments. Some are ejected from the solar system entirely by gravitational kicks from the planets. To maintain the brilliant pillar of light we see, there must be a massive, ongoing source pumping new dust into the system at a rate that far exceeds what our traditional models allow. For decades, the prime suspects have been comets and asteroids. As comets swing around the sun, their ices vaporize, releasing trapped dust and gravel to stream behind them in magnificent tails. Asteroid collisions, too, can generate enormous clouds of debris. Yet, when we add up all the potential contributions from every known comet family and asteroid belt collision, the numbers still fall short. There is a missing dust factory operating somewhere in the inner solar system. The search for this factory led astronomers on a meticulous hunt, and a major breakthrough came from an unexpected direction: an asteroid survey telescope. While the Solar Terrestrial Relations Observatory, or STEREO, was primarily designed to study the Sun, its cameras also captured the vast expanse of space around it. As scientists sifted through its data, they weren't just looking for asteroids. They were also mapping the intricate structure of the zodiacal dust cloud itself. To their astonishment, they discovered not a smooth, homogeneous cloud, but one with distinct groupings and concentrations. Most remarkably, they found two vast, dense bands of dust that were not centered on the sun, but were instead gravitationally shepherded, trailing along the orbit of the planet Venus. This was a revelation. Here was a previously unknown massive reservoir of dust co-orbiting with our sister planet. The immediate question was whether Venus itself could be the source. Could volcanic eruptions or massive impacts on the planet's surface be launching enough material into space to create these bands? This seems highly unlikely. Venus's immense gravity and thick atmosphere form a formidable barrier, making it extraordinarily difficult for any surface material to achieve escape velocity and enter a stable orbit. A far more compelling theory suggests that this dust is not from Venus, but is merely trapped by it. The gravitational pull of a planet can create stable zones ahead of and behind it in its orbit, known as Lagrangian points, where dust tends to accumulate. The leading hypothesis is that this dust originates elsewhere, likely from the ongoing disintegration of a much larger population of dark, dusty comets or asteroids that we have yet to fully catalogue, and that Venus's gravity acts as a celestial shepherd, gathering and corralling this debris into these dense, glowing bands. This discovery provides a crucial piece of the puzzle, potentially accounting for a significant portion of the missing mass. Yet, even with this newfound source, the paradox may not be fully resolved. It's possible that the Venusian dust bands are just one component of a much larger and more complex dust production system. There could be other, similar reservoirs tied to the orbits of other planets waiting to be discovered. Furthermore, our understanding of the dust production rates from comets might be fundamentally flawed. We may be underestimating the sheer number of small, dark comets that plunge into the inner solar system, shedding their dusty coats before disintegrating unnoticed. The zodiacal light, that soft and seemingly peaceful glow, is therefore a testament to an unseen, violent, and ongoing struggle within our solar system. It is the glittering evidence of countless collisions, evaporations, and gravitational captures, a dynamic and dusty ecosystem that we are only just beginning to measure and understand, reminding us that even the spaces between the planets are teeming with activity and mystery. But if black holes and the dusty glow of our own system present puzzles of existence and abundance, there is a star system just 40 light-years away that offers a different kind of mystery altogether, one defined not by what we have found, but by a profound and unexpected silence. In the constellation of Aquarius, a dim, red ultra-cool dwarf star named TRAPPIST-1 hosts what is arguably the most tantalizing planetary system ever discovered beyond our own. Around this star, which is only slightly larger than Jupiter and about 1,000 times dimmer than our Sun, orbit 7 known rocky worlds. 3 of them, TRAPPIST-1e, F, and G, sit squarely within the star's habitable zone, that Goldilocks region where temperatures could be just right for liquid water to exist on their surfaces. When this compact family of Earth-sized planets was revealed, it sent a wave of excitement through the scientific community and the public imagination. Here was a system that seemed to check all the boxes for a potential cradle of life and even intelligence. It instantly became one of the primary targets in the search for extraterrestrial intelligence, a beacon of hope in the vast quiet of space. Yet, when we turn our most powerful listening devices, radio telescopes like the Green Bank telescope, toward TRAPPIST-1, we are met with nothing but an empty static hiss. The great silence of TRAPPIST-1 is a mystery that forces us to confront the daunting challenges of cosmic evolution, reminding us that a planet being Earth-sized and in the right place is only the very beginning of the story. The first and most defining feature of this system is its breathtaking compactness. All 7 planets orbit their star at a distance smaller than Mercury's path around our Sun. The innermost world completes a revolution in just a day and a half, while the outermost takes about 20 days. This proximity has a profound consequence: tidal locking. Just as our moon always shows the same face to Earth, it is almost certain that every planet in the TRAPPIST-1 system has a permanent day side and a permanent night side. Imagine a world where one hemisphere is locked in eternal, blistering daylight, while the other is frozen in an endless, star-filled night. The only potential for a temperate environment would be in the thin, razor-sharp twilight ring along the terminator line between these two extreme zones. On such a world, weather patterns would be unlike anything we know, potentially featuring hurricane-force winds screaming from the hot side to the cold side in a desperate attempt to balance the incredible temperature differential. The stability of any atmosphere under such relentless and uneven stellar heating is a major question mark, as the atmosphere could itself freeze out on the cold, dark side, leaving the planet a barren, airless rock. Adding to this environmental challenge is the temperamental nature of their parent star. Ultra-cool dwarfs like TRAPPIST-1 are notorious for their volatility. While they can shine with a steady warmth for billions of years, they are also prone to frequent and violent outbursts, superflares, and coronal mass ejections that can be hundreds of times more powerful than anything our Sun produces. A young, life-giving planet in this system would not be gently warmed by a nurturing sun, but repeatedly scalded and sterilized by these apocalyptic blasts of high-energy radiation. Such flares would not only threaten to strip away any developing atmosphere, but would also bathe the planetary surfaces in ultraviolet and X-ray radiation capable of breaking down complex organic molecules and eradicating any fledgling life forms that might have taken root. For life to survive here, it would need to be extraordinarily resilient, perhaps existing deep underground or underwater, completely shielded from the violent tantrums of its stellar parent. This leads us to the heart of the silence. Given these immense challenges, the quiet we hear from TRAPPIST-1 might be a simple answer: the system is sterile. The combination of tidal locking and intense stellar activity may have created an environment too unstable for life to ever gain a foothold, let alone evolve into a complex technology-building civilization. The Great Silence could simply be the silence of a collection of dead rocks, fascinating for their architecture but ultimately barren. However, another possibility is far more haunting. Perhaps life did emerge on one of these worlds, and perhaps it even evolved into intelligence, but the very nature of their stellar environment could have made the development of a technological civilization nearly impossible. How does an intelligent species discover radio waves if its atmosphere is constantly being ionized by stellar flares, creating a permanent and impenetrable barrier to long-range communication? How does a culture develop astronomy if its sky is forever dominated by the terrifying glare of a giant, angry red sun and the looming specters of its sister planets, with no view of the broader cosmos to inspire curiosity? Their entire cosmological perspective would be fundamentally different from our own, potentially limiting their technological trajectory in ways we cannot even conceive. The silence might also be a matter of timing. We have been listening for a cosmic heartbeat for less than a century. An alien civilization around TRAPPIST-1 might have risen and fallen billions of years ago, their signals having long since passed us by in the depths of space. Or their era of broadcast technology might have been incredibly brief, a fleeting whisper in the cosmic din that we simply missed. The TRAPPIST-1 system, in all its promise and peril, stands as a powerful lesson in humility. It shows us that the universe is not obligated to provide ideal conditions for life as we know it, and that the path from a habitable zone to a humming civilization is likely fraught with far more obstacles than we have previously considered. Its silence is not a disappointment, but a crucial data point, compelling us to broaden our definition of habitability and to listen more carefully, not just for signals we expect, but for any sign that something, against all odds, has found a way to endure. Yet, even as the silence of TRAPPIST-1 reminds us of the profound challenges of life, the very foundation of our cosmic understanding is being shaken by a discrepancy so fundamental it calls into question the rate at which the entire universe is growing. This crisis, known as the Hubble tension, isn't a minor accounting error. It's a full-blown schism in cosmology, a stubborn rift between two impeccably crafted methods for measuring the universe's expansion rate. For nearly a century, we've known the cosmos is stretching, with galaxies receding from each other as space itself expands. The speed of this growth is encapsulated in a single, crucial number, the Hubble constant. Pinpointing its value is arguably the most important goal in modern cosmology, as it tells us the universe's age, its ultimate size, and its final fate. The shocking problem is that our two most precise and trusted ways of measuring it are giving us answers that stubbornly, definitively refuse to agree. On one side of this great divide, we have a method that peers back to the universe's very infancy. The European Space Agency's Planck Space Telescope spent years mapping the cosmic microwave background, the faint afterglow of the Big Bang, with breathtaking precision. By studying the tiny temperature fluctuations in this ancient light, the frozen ripples from a time when the cosmos was just 380,000 years old, cosmologists can use our well-tested model of the universe, known as lambda cold dark matter, to work forward and predict what the expansion rate should be today. This is a measurement rooted in the pristine physics of the primordial universe, and it gives us a value of approximately 67.4 kilometers per second per megaparsec. A megaparsec is a staggering 3.26 million light-years, so this value means that for every additional megaparsec of distance, a galaxy is moving away from us 67.4 kilometers per second faster. On the other side of the divide, we build a cosmic distance ladder right here in our own galactic neighborhood. This technique, championed by the SH0ES team, uses incredibly reliable stellar objects as standard candles. The most crucial among them are Cepheid variable stars, whose intrinsic brightness pulses at a rate directly tied to their true luminosity, and Type Ia supernova, the thermonuclear explosions of white dwarf stars that all reach the same phenomenal peak brightness. Because we know their true brightness, measuring how dim they appear from Earth allows us to calculate their distance with tremendous confidence. By then measuring the redshift of their host galaxies, how much the expanding universe has stretched their light, we get a direct local measurement of the Hubble constant. This painstaking step-by-step calibration yields a value of 73.2 kilometers per second per megaparsec. While a difference of about 5.8 units might seem small, in the world of high-precision cosmology, it is a colossal and unbridgeable chasm. The uncertainty margins for both methods have been shrunk to such a degree that the disagreement now stands at a confidence level of over 5 sigma. This means there is less than a 1 in a million chance that this is a mere statistical fluke. This isn't an error bar overlap, it's a direct contradiction. For over a decade, scientists have exhaustively searched for a mundane explanation, a hidden systematic error in one or both methods. Could the Cepheid distance scale be subtly miscalibrated? Could there be unknown dust obscuring the supernova? After years of intense scrutiny and improved measurements, the error bars have only tightened, making the discrepancy more significant, not less. This persistent tension is a powerful indicator that the problem isn't with our measurements, but with our model. Our standard model of cosmology, Lambda CDM, which has been spectacularly successful for decades, appears to be missing a key ingredient. This realization has launched a new golden age of theoretical physics, as cosmologists propose fascinating and sometimes radical new ideas to explain the tension. One leading possibility involves a new, transient form of early dark energy. This theory proposes that a previously unknown energy field briefly flickered into existence in the first few 100,000 years after the Big Bang. This extra dose of repulsive force would have subtly altered the way sound waves propagated in the dense early universe, changing the cosmic ruler used to measure the CMB. This adjustment would lower the predicted expansion rate from the Planck data, potentially bringing it into line with the higher local measurement from SH0ES. Other theories suggest that dark energy itself is not a constant, as in Einstein's cosmological constant, but is instead dynamic. This concept, called quintessence, posits that the energy causing the acceleration of the universe could be evolving, growing stronger over time, and thus speeding up the expansion more than our current models anticipate. There are even more exotic proposals on the table. Some physicists are re-examining the very fabric of gravity itself, wondering if Einstein's theory of general relativity requires modification on the largest cosmic scales. Perhaps dark matter isn't completely cold and non-interacting. Maybe it can interact with itself or with radiation in ways we haven't yet considered, which would alter the growth of cosmic structure and impact the expansion history. Others have even entertained the idea that our universe is not perfectly flat, but is ever so slightly curved on the largest scales, which would subtly warp our measurements and calculations. The Hubble tension is more than just a numbers game. It is the universe itself pointing toward a gap in our knowledge, a glaring signpost that there is new physics waiting to be discovered just beyond the edge of our current understanding. Resolving this crisis will require next-generation telescopes like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, which will provide an avalanche of new data to test these wild new theories. This discrepancy is the most important unsolved problem in cosmology today, and its resolution promises to unveil a deeper, richer, and even more surprising cosmos than the one we think we know. From the ghostly tug of the Great Attractor and the invisible scaffolding of dark matter to the repulsive force of dark energy and the fleeting wow signal, these 25 cosmic mysteries represent the very frontiers of human understanding. Each one is a testament to the universe's profound capacity for wonder, challenging our most fundamental assumptions and pushing the boundaries of what we believe is possible. Consider the violent, energetic flashes of fast radio bursts, the bizarre dimming of Tabby Star, and the perplexing motion of the Pioneer probes. Each anomaly, each discrepancy, is not a failure of our models, but a beacon guiding us toward a deeper, richer truth. These puzzles are the engines of scientific progress, driving technological innovation as we build ever more sensitive telescopes, dig deeper underground for elusive particles, and launch sophisticated probes to the far reaches of our solar system and beyond. They remind us that the cosmos is not a static painting to be observed, but a dynamic, evolving story that we are actively deciphering. The Hubble tension threatens to rewrite our cosmic timeline. The Kuiper cliff hints at unseen worlds, and the missing lithium from the Big Bang points to physics operating in the universe's first seconds that we have yet to comprehend. Even the haunting silence from the TRAPPIST-1 system speaks volumes, forcing us to broaden our definition of life and our place in the grand scheme of things. From the geometric perfection of Saturn's hexagon to the information-devouring paradox of black holes, these mysteries show us that curiosity is our most valuable tool. They underscore a beautiful truth: the more we discover, the more we realize how much is left to explore. This journey through the cosmic horizon is ultimately a reflection on humanity's place in the vastness of space and time. We are a young species on a small planet, yet we dare to ask the biggest questions and reach for the stars in our quest for answers. Every mystery solved doesn't simply provide an answer, it opens 10 new doors, ensuring that the adventure of discovery will never truly end. The universe is a puzzle with an infinite number of pieces, and we have only just begun to fit a few of them together. Now, we'd love to hear from you. Which of these 25 mysteries captures your imagination the most? Is it the potential for life on Mars, the enigma of Oumuamua, or the unsettling alignment of the axis of evil? Share your thoughts in the comments below, and if you enjoyed this voyage to the edge of understanding, be sure to subscribe for more content that explores the greatest wonders